Hi, my name is Michael Hill. I'm with the live video team at Twitter. You guys all here? And we're going to talk about audio today. A little variety from, we've heard a lot about video, so we're going to have a little variety today. So this is a development story about a feature we built for Twitter and Periscope live video about a year ago now. And it's a stateless system for audio processing. I didn't get my clicker. Where's my clicker? Do I get a clicker? I'm waiting for my clicker. So theoretically, there are more slides here. Thank you. All right. So so stateless system for audio processing. So when I say stateless, what am I really talking about here? Because you could have a number of different definitions for that. But for the context of this talk, a stateless service is something that generally has short requests, so a few seconds long. A stateless service would not require context to do its job. So if I send you a request, I'm going to send you all the information that you need as the service to do what you need to do and send me back the response, and not really depend on the fact that I've called the same instance more than once or anything like that. So I don't have to store any data on there, make any calls, anything like that. And a stateless service also can typically be deployed quickly because engineers like to deploy things fast. We like to make changes, and it's nice to not have to wait a long time before your critical bug is fixed. Stateful service, on the other hand, is something that can have long-running connections, a minute, hour, day. So you really don't know how long live connections are going to be running on that service. Can have contextual information. So a stateful service can have information that depends on the fact that you call the same instance more than once, can depend on something over time, data being stored on that instance. So it can be a little tricky, and can also potentially take a long time to deploy. We have one of our services can take upwards of 3 days to deploy because we have requests that can last up to 24 hours. We deploy it a third at a time. And we have to wait for any live traffic on there to drain off of the instance before we can deploy new code on there. So that's something that we'd like to get that way down if we can. So stateless is cool. I like stateless. So how does this relate to our Twitter live video feature? So when you go live on Twitter, you grab your Twitter app, your Periscope app, and you hit the Go Live button. And after that, you are sending your video and audio samples through our magical Twitter Live infrastructure. And somewhere in there, we're taking those samples. We are putting them into segmented media for distribution over HLS. So segmented media files, playlists, and we can distribute over HLS and LHLS. We try to keep our latency as low as possible for our broadcast because we have chat window, and the viewers will interact with the broadcaster through chat. So we want to keep the latency low enough that the broadcaster can react to chat messages in something close to real time. So that's going live on Twitter. In a little more detail, we have a broadcaster. So in this case, it's a mobile app. We make a TCP connection to our Ingest server. Ingest server talks to the broadcaster over RTMP. And you're sending your video and your audio to the Ingest server. And on there, we have a playlist builder. We have a media segmenter. The samples go into media segments, stored in Redis for live playback. We store the information we need to build playlists also in Redis. We have another service called Media Origin Service that sits between the rest of the infrastructure and the CDN. And then viewers can pull playlists and media segments that are generated for them, and they will be able to play back in HLS or LHLS. So we have an ingest segment, we have a processing segment, and we have a playback segment, and we have happy viewers, hopefully, and hopefully a lot of them. So that's what we have right now. That's for a broadcaster using our infrastructure. And we wanted to add a new feature. So we're calling it Conversational Broadcasts. So essentially what this is we wanted to give our broadcasters the ability to invite guests to call into their broadcast, like a call-in show, talk show kind of situation. So a guest can call in, a broadcaster can invite them, or they can request to join the broadcast. And now they're having a live conversation, and that is something that we want to take their live conversation and broadcast it to as many people as want to view the broadcast. So we have one main broadcaster, and we have up to 3 audio guests for this feature. Each of the participants in the broadcast is running a WebRTC client. They are forwarding their media to a selective forwarding unit. So that, for the main broadcaster, the video and audio is being sent there. The rest of the participants, just their audio only. And then everyone gets a copy of everyone else's stream. So they are interacting with each other in a video conferencing style situation, interactive latency about 200 milliseconds. So now we have to figure out how this is going to fit into our existing infrastructure and to be able to eventually get this all into HLS and LHLS so everyone can view it. So now instead of a single broadcaster sending their media samples over RTMP, we now have multiple participants sending media over RTP to selective forwarding unit. Now that is forwarding everybody's streams to our ingest server, same ingest server, but now that's RTP over TCP coming in there. And we have a mysterious new component of audio processing, which is the main body of what we're kind of talking about here. And once we do that mysterious audio processing, we go back in there, we build our playlists and our segments, and everybody can watch the video, and they're very happy about it. So now what is this audio processing thing, and why do we actually need it? We didn't need it before with a single broadcaster. And that was mainly because we have, there's one mobile app sending over RTMP, sending AAC encoded audio to our ingest server. And we can take that directly and mux it into media segments, and we don't need transcoding. We're going straight from AAC into HLS and HLS playlists. So in that case, we did not need a separate processing step. But now we're using WebRTC, and WebRTC by default uses Opus audio codec. And HLS by default wants AAC audio codec. So in order to make this work, we're going to need a transcoding step somewhere in the pipeline. In addition, we have multiple audio streams instead of just one. So we want to keep those synchronized. We want to make sure that conversations still sound conversational, things happen in the right order, and we want to handle these multiple audio streams during playback nicely. So multiple audio stream processing. We're going from one to many. What does that mean? Do we handle that on the player or the backend? We have a decision to make. So let's imagine we're going to try to do this on the player side. There may be some advantages to doing this. That would mean that you still have individual control over these streams at the player side. You might be able to mute an individual participant on the player side, or they're still separate, so there might be some advantage there. So how would we do this? So basically we take each individual participant's audio, keep it in a separate HLS audio playlist, and then on the player side, our plain vanilla HLS player would not be able to handle these multiple audio playlists. So we'd want to launch multiple HLS audio players, and they'd be kept in sync by an external sync mechanism. So something that's adjusting the timing of each player in real time to try to keep them together. So doable. This is something we could build. After a little bit of experimentation, what became evident is we have a lot of different players. We have Periscope app, we have Twitter app, we have web, all of which have different HLS implementations. And we have different platforms, iOS, Android, et cetera. So quickly became evident that this was going to be a significant development hurdle, and it was worth it to look into an alternative here. So specific alternative is a single mixed audio track. So take your Opus audio. This would live on the server now. This would live in our audio processing component on the server side. So take your Opus audio tracks from your WebRTC clients as they come into your ingest server, forward them to your audio processor. Now they all arrive at the same place. They arrive at a mixer where we combine everything into one mixed audio track, re-encode into AAC, and now we can go back into HLS land, and we're happy. So we kind of outlined what we need to do at this point. We need to take our Opus audio, decode it into raw audio samples, mix our multiple audio tracks down to one, re-encode back to AAC, and then send our result back to the requester. So that's kind of the outline of what we need to do in our audio processor. So another decision point here is when we're designing our audio processor, do we make this a stateful or a stateless service? So if you wanted to go for the simplest implementation here, one very simple solution would be to fire up an instance, run a single audio processor for the entire duration of the broadcast. So yeah, one broadcast, keep the connection open, send audio there, do the processing, and send it back. So that has an advantage. It's pretty simple to implement. There's a lot of details that you don't have to worry about. You don't have to worry about reconnections, anything like that. And you have all the information you need right there in order to run your whole audio process for your whole broadcast. But there's a significant drawback. This is now, because it's a stateful service, it would be a long-running connection. You would not be able to easily switch instances or redeploy the service with a predictable length of time, mainly because you'd have live traffic running on there and you wouldn't want to just cut it off in the middle. Or you would, in fact, if you did, in fact, switch instances, you would have missing audio in there because we're not accounting for that. That's a form of state that's propagated in here that we would not be taking care of. So yeah, we could do that. And maybe you could just run this whole thing on the ingest server. That would be simple, right? You don't even need a new piece of infrastructure. Well, you could do that. We chose not to do that partially because of a separation of concerns. We basically wanted to keep our services relatively small, relatively specialized, and not mix up too many features in there. It just becomes harder to debug and more points of failure. And also this represents, if we did do that, we'd have a stateful audio processor on our stateful ingest server. It's more state in an already stateful service. So we have a goal for the future to basically make more things stateless, including that ingest server. So by just adding more state here, we're making that more difficult on ourselves in the future. So some things to consider there with that decision. Clicky. Hello. No clicker problems here. Do we have another click? Oh, there we go. Cool. So this is the alternative. This is the alternative we outlined for ourselves. So this is essentially the stateless option, the client-server audio processing. So we're going to make this, to basically break up the job and make it more stateless, we're going to handle the audio in small batches. So instead of just one long-running process that just takes all the audio in, sends all the audio out, we're going to chunk it up into small chunks, a few seconds long, even shorter than a few seconds long. And we're going to separate the duties out into a client and a server. So the client is something that's going to live on our ingest server. That's going to remain a stateful component for now. And then we have a stateless component on a separate instance. So that's going to be our audio server. So basically, we're going to send little bits of audio to it. It's going to do everything we need: decode, mix, encode, and send back. So by doing this, we essentially break up the job into short chunks so we can speed up our deploy times and be happily stateless. So we're done, right? We have short, independent requests. We're stateless, and everything's great. And the talk is finished, right? Well, you probably guessed it's not finished. There's a little bit of a complication. So AAC and among other audio codecs use what's called a lapped transform. I'm not going to go into the deep details of it, but essentially lapped transform is something that introduces dependency both in, it has a bidirectional dependency based on a window function here. So if you want to accurately reproduce a sample at a given time, you need audio information from both the past and the future. So the implication here is that encoding audio chunk-wise like this becomes not entirely an independent operation. You actually have a dependency on a little bit of audio from the previous chunk of audio in order to warm up the encoder, get the AAC encoder into a state where it's going to accurately reproduce the first sample of your chunk without introducing audio artifacts. And if you don't do this, yeah, you're going to have gaps. You're going to have audio artifacts at the beginning of each little chunk of audio that you encode. So this is an element of state that we need to handle here. So we need to be able to deal with this little bit of AAC priming audio every chunk. Okay, so let's go over. So now we've separated out our duties into a client and a server, and we're going to kind of explore how everything works and how we handle this, this dependency on priming audio. So this is the client side. This lives on our stateful ingest server. Coming into that will be the WebRTC Opus audio from our WebRTC clients and the participants of the broadcast. These are samples coming in from different participants, each marked with a different timestamp. They can arrive out of order. Fundamentally, things are arriving over RTP, so we can have dropped packets, and we can have out of order packets coming in. So they arrive in the order that they arrive, and then they get pushed into an audio processing client. The first stage of that client is approximately 1 second buffer, where we buffer up these input samples. The length of the buffer can be adjusted, but basically this is a component which will add it'll add 1 second to the latency of the overall system. So we don't want to increase that too much. So you can adjust that value based on how much latency you want to add to the system, balanced against how much leeway you want to give for late packet arrivals. So we have the 1 second buffer. We reorder, and now we have a request loop that runs in the client, and periodically that will take well-aged audio past 1 second out of the buffer, and it will create audio chunk requests to be sent to the audio server. So in this case, we're sending a request to encode chunk 2. So we have the body of chunk 2 there, and we have the priming audio from the end of chunk 1 that we're sending in a request. So we send this request along to an audio server. Audio server streams back the response as mixed AAC audio. When this arrives back, we basically look at the timestamp of the audio coming back, and now we know that we have chunk 2. We have the mixed audio from chunk 2 coming back. So now we can get rid of chunk 1. We no longer have a dependency of chunk 1, but we actually need to keep chunk 2 for a little while until you encode the next chunk. So we need the end of it in order to satisfy that priming audio requirement. So this is on the client side. So this is the transport between client and server. We're using chunked HTTP transport, a slightly hacked up version of chunked HTTP transport. So chunk transfer encoding. So we are, instead of sending it basically looks like a post request, but instead of the normal way a post request happens, where you send the entire post body arrives and then you send the entire response, we are doing it a little bit at a time. So the post request comes in, the response streams back as soon as the mixed audio data is available. So this is basically it's a slightly hacked up post request that looks like a TCP socket or WebSocket behavior. Could be implemented with one of those, but we did it this way. So, and in this, so we have this, the chunked transport here means that we're not waiting for an entire chunk of audio, an entire chunk of audio of a few seconds to arrive at the server before we respond, and therefore avoid adding several seconds of latency to the system. So we add in the order of milliseconds of latency by doing this during the network transport. Okay, the other side of it, audio processing server. So this lives on its own instance, has an HTTP front end, and it allows short requests. So about 5 seconds is the maximum amount of time that you can make a request to this audio processing server, and it will just cut you off when you've gone too long. And the client is responsible for dealing with being cut off from the audio processing server. And it processes audio one chunk at a time as it arrives. So we have here an example HTTP request that's coming into the audio processing server. Previous chunked audio comes in for AAC priming from multiple participants. You have a start timestamp that indicates the beginning of the chunk you want to send back, and then you have the actual audio for the current chunk. And so then on the same box we have our own transcode processing executable in an FFmpeg style. Basically we wrapped the encoders and decoders with our own executable, and we have a bespoke media streaming protocol, which is basically a container format plus a command format in the same box here. So we're sending in instructions to the decoders to initialize themselves, and we're sending audio media packets as well. So we send our chunk audio. We have a bank of Opus decoders. We have a mixer now, and then we have an AAC encoder, and then we send back the response with our nicely mixed and encoded audio. So the mixer itself, so this basically covers everything up to the actual audio processing that we're doing in that mix component. So when audio arrives at this audio server, we line it up based on its timestamps, and now we have essentially a grid of audio chunks from all the participants lined up at the right times. And we want to actually do, now, what do we actually do with this audio? We want to turn it into a single audio track, but that's a whole subject in and of itself. Well, what's the right way to do mixing here? So our original intent was to do some forms of stateful audio processing. So imagine the most obvious one that we wanted to do was an automatic level control system. So basically one participant's talking really loud, one participant is whispering, and we want to kind of level their audio as much as possible and be able to have the mixed audio sound reasonable, where everybody has close to the same level as possible. So that's something where we can take, we have a chunk that's loud, we can attenuate it, we have a chunk that's quiet, we can bring it up. The reason this becomes stateful now is that when the one chunk is complete and we have another one, we're going to want to propagate over the last value of that coefficient, for example, because we don't want to have a big jump in level between segments. So if I'm just starting a new, fresh audio chunk and I don't know the last multipliers for every participant, then it'll be difficult. Then we could have a jump in audio, and that wouldn't be great. The other big advantage of having this audio processing component is if you did want to make a robot voice, this is the place you'd do it. We did not, in fact, do it there, but that's where you'd want to do it. So what we did do is a fairly simple solution. Has its implications, but we simply decided let's just take all the audio, let's just add it up and see if it clips. So we basically take our lined up audio, we go sample by sample, add them all up, and in the case where it does exceed the boundaries, the +1, -1 boundaries of our output audio signal, we'll just cap it at +1, -1. We'll let it clip. So this is something, if you add up a bunch of audio signals, you're going to have clipping. That's going to be a negative audio artifact that you might introduce. But what we found is for the type of content we're dealing with here, spoken word conversations where primarily one person is talking at a time, generally we don't have that many clip events. It's fairly rare for spoken word content that we see here. And when the clip events do happen, it's generally when everyone's talking over each other, and it's not the greatest audio to listen to anyway. So this is something, if everybody had synchronized full amplitude sine waves, yeah, you'd have a lot of clipping. But in our case, we decided to try it the simple way. It has the advantage where it's a stateless operation. Doesn't require any propagated state between audio chunks. So that's more or less the audio system that we're dealing with here. So what's next? What are we going to try to do next here? Well, ideally, we'd like to make more of our system stateless and remove that dependency, that long deploy time. So we're going to try to make, we'd like to try to make our ingest server stateless. And in order to do that, one component of that is to make this audio client itself stateless. So currently, what happens is that audio client needs to retain a certain amount of audio to do the AAC priming audio for upcoming chunks. So what we'd like to do is write any changes in state to the client to a persistent storage like Redis. Essentially, update a key value when we have key events that mutate our state. So new audio arrives from WebRTC. We would change our key value. Or processed audio returns from the audio service. We would also do that. So in the case that the server did melt down or whatever, server goes down, we can just fire up another one, read the state back from Redis, and we can continue. So that's a goal upcoming, is to make more things stateless. And that's it. Thank you.